I will today talk about the paper Effective Communications, a joint learning and communication framework for multi-agent reinforcement learning over noisy channels. The paper was published by the Information Processing and Communications Lab of the Imperial College in London. Before I want to start with the topic, I will give you a quick overview about the stuff I will be talking about and give an outline about this presentation. I will start with a quick motivation on why this topic is interesting for science. Then I will head over to a brief summary or introduction to communication theory in general, especially for the ones of you who've not heard too much about this topic already. Then I'll head over to the problem formulation, so explaining which problem they want to tackle in this paper, and then I'll explain the two applications that they experiment with in the paper, and then I'll conclude with my talk. Communication is among the most important things for our society. We humans use language to communicate ideas, and this gave rise to the complex social structures we are living in now. Also, scientists have observed vocal and gestural communication in other animal groups, and there's also studies that suggest that an increased complexity in communication goes hand in hand with complex social structures. One of the most important things, though, is that communication helps us achieve complex goals by enabling us to cooperate and coordinate with each other. And by now, communication technologies are probably the core of our connected society. Our communication technologies are built upon mathematical principles and engineering expertise. So engineers found reliable ways to transmit messages over channels using advanced technologies like networking protocols, modulation techniques, waveform designs, and advanced coding techniques. This approach, though, ignores the core objective, which I mentioned before, of cooperation and coordination. So we've always been separating between the communication network itself, transmitting the bits and information, and the language that we speak and that is formed to achieve coordination among the agents using that language. This was already highlighted by Shannon in 1949, who organized the communication problem into three distinct levels. There's level A, the technical problem. It asks the question of how accurately can the symbols of communication be transmitted. So it's actually the technical question of how well does the receiver decode my message. Then there's level B, which is called the semantic problem. It's more of a language thing. So how precisely do the transmitted symbols convey the desired meaning? And then there's level C, which is the effectiveness problem, and it asks how effectively does the received meaning effect conduct in the desired way. So does the message I'm sending influence the receiver in the way that I want him to behave? In this paper, the authors mainly focus on level C, which is kind of the broadest formulation of this whole communication problem. And it also generalizes the level A and B, because if we effectively communicate and if we solve that problem, we implicitly solved level B and A already. The goals and contributions of this paper. So the authors are going to formulate the effectiveness problem mentioned before in terms of agents communicating over a noisy channel in order to cooperate and coordinate their tasks. This is also referred to as joint communication and learning approach, because the agents are learning to communicate and learning to solve their task at the same time. After formulating the problem, there will be a proposition for a framework that models exactly the scenario, and also it models the communication link between the agents really realistically. In the end, the problem will also be put into another setting, so it can be used to provide alternative approaches to the technical problem. So that means just designing codes and communication schemes, and then the learning to solve tasks will be put aside, and the focus is more on the communication side. Okay, so now I will start with some basics in communications for everyone who has not had a lot of experience in this topic. So this is the typical communication model, where we have on the left side an agent with some information that they want to transmit. So they have an encoder that encodes the message they want to send into an electronic signal, and the signal is sent over the channel. On this channel, there can happen a lot of things. For example, if we have a wireless channel, there's a lot of interference going on and stuff like that. So we model this as a noise source, which is put on top of the signal that the agent 1 sent, and the receiver, the agent 2 in this example, will try to decode the received signal and recover the message that agent 1 has sent. To put this a bit more into a mathematical formalism, we can say that information of B symbols will be coded into a message of length m. That means the transmitter will choose m symbols from their alphabet in order to encode the information that they want to send. This encoded message will then be sent over the channel. The code rate will be b over m, and we have m minus b redundant symbols that can be used later on or on the receiver side for error detection and correction. Okay, now we talked about the general communication model. Now I want to talk about 3 different channel models that were used in this paper to simulate realistic communication. Probably the most simple model of a channel, and probably every one of you has seen it already at some point, is the binary symmetric channel. So that means we have an input and an output alphabet consisting of just zeros and ones, and we have a probability that a bit that was a 1 now flips to a 0, or the other way around. This is called the crossover probability and is denoted as P here. The message at the receiver side is basically just the message on the transmitter side, XOR our noise term, which comes from Bernoulli distribution. The next channel model is the additive white Gaussian noise channel, which models interference of multiple users, and usually it is used for modeling a wireless channel. Here our noise term comes from the Gaussian distribution with 0 mean and sigma n as the covariance term. The message on the receiver side is basically just the message that is transmitted plus the noise. There's different options for the transmitter alphabet. There's technologies that are limited to beat phase shift keying, which means they can only use zeros and ones to encode a message, but there's also transmitters that have no limitation on the input cancellation and can use just symbols from the world of the real numbers, but then it usually imposes an average power constraint because transmitter doesn't have unlimited power. The receiver alphabet is always the real numbers, because even if I have only 0 and 1, if I add on the Gaussian noise, it will become a real number. And then the third channel model is the burst noise channel, which is kind of just an extension of the additive white Gaussian noise channel, but it has 2 states of noise, which should model an occasional high interference with a very close transmitter. So our message on the receiver side is again the message on the transmitter side plus our noise term, and the noise term is now either a high noise or a low noise term, and this is modeled by a 2-state Markov noise. Now we get to the problem formulation. So how do we formulate the problem of communication such that it can be tackled with algorithms from reinforcement learning? So we first formulate a partially observable Markov decision process for multiple agents. So this introduces a Markov game consisting of the state space S, the observation of n agents, the action of n agents, the state transition kernel P, and the reward function R. So at step T, every agent has the partial observation and takes one action. Afterwards, the state transitions to the next state according to the transition kernel, which is dependent on the state and the joint actions of all agents. Each agent afterwards receives the reward R, so everyone gets the same reward, and we call this the fully cooperative setting. In order to better coordinate and cooperate, the agents are endowed with a noisy communication channel. So this gives some modifications to the partial observable markov decision process that we defined before, and that is that each agent now not only observes the state of the space, but also observes a message that they receive, and they not only select an action that's acting on the environment, but also select an action that they want to send to the other agents. All this is according to the joint policy, which is defined as pi from the whole state space, including the messages that they receive, to actions acting on the environment, and as well messages that they want to send. As usual, for our reinforcement learning setting, the goal is to maximize the discounted sum of rewards, and we can also define the Q function, which we will be used to exploit the learned policy. It should be emphasized that the channel is orthogonal to the environment. That means that the state transitions only depend on the actions taken and not on the messages sent. And we can say that this is a very general framework that could be used for very complex multi-user settings, but here the main focus will be on point-to-point communications in order to demonstrate the benefits of joint learning and communications over simple experiments where they learn to communicate and to behave in a separate way. We will now come to the first application shown in the paper. In order to demonstrate the learning framework, we will construct a simple example, namely the guided robot with point-to-point communications. We will use a single agent markov decision process and turn it into a multi-agent partially observable markov decision process just by dividing a single agent into two separate agents. Those two agents are namely the guide, which communicates through the noisy channel with the second agent, which is called the scout. The guide observes the environment perfectly but cannot take any actions directly on the environment. On the other hand, the scout can take actions but does not observe the environment at all. So all actions that are taken by the scout are only dependent on the messages sent by the guide. Without the messages, the scout would take purely random actions, and this would not lead to a high reward at the end. This experiment will allow us to quantify the impact of channel noise, because if we have a perfect communication link, then the original single agent markov decision process will be recovered, or it should be recovered in theory. We consider a grid world in which the scout can take actions. The scout position at each time step is denoted by their horizontal and their vertical position on the grid, and the scout can take 16 different actions that are illustrated in the picture on the right. The objective for the scout is to find a treasure which is located at the goal location as quickly as possible. We assume that the scout location and the goal location isn't initially the same, and they are sampled randomly. And also our environment isn't fully deterministic, but with a certain probability the scout will land on a neighboring cell of the one that he originally intended. Okay, now we talked about the setting of this problem. Now I would like to put this guided robot into the context of the problem formulation of the multi-agent partially observable markov decision process. So agent 1, which is the guide, observes the state of the environment, namely the position of the scout and the position of the treasure. And the guide has the action set of sending M symbols from their transmitter alphabet. Agent 2, namely the scout, observes this message that was sent previously by the guide by the guide and takes an action that is toward 2 steps or 1 step. The game will terminate when the scout location and the goal location is the same, which means the scout found the treasure. And the reward function, which encourages the 2 agents to collaborate and cooperate, is it will get 10 points if the scout location is equal to the goal location and -1 if it isn't. If the scout tries to step outside of the grid, it will just remain at its original position. Now we come to the algorithm for the case where the 2 agents are communicating over the binary symmetric channel. So that means the action of agent 1 will be to transmit M symbols of either 0 or 1, and the receiver will again receive those symbols, but maybe there's some bit flips inside, and that's the observation which the agent will base its decision on. To make good decisions and to maximize the reward, we will employ deep Q learning to learn the Q functions of both agents. So we will use 2 distinct deep neural networks, which are parameterized by θ1 and θ2 for agent 1 and agent 2 respectively. As typical for Q learning, the algorithm makes use of replay buffer, target networks, and the epsilon greedy strategy. So replay buffer stores the observation taken by agent I, the action taken, and the reward that they are rewarded together, and also the observation it will make in the next step. The DQN loss function is defined as the squared difference between the reward plus highest Q value of the next step and the Q value for the current state action pair. The target network parameters are updated with a certain delay, which is reflected in the parameter tau. Now we will come to the first algorithm, which is proposed as a solution for the guided robot problem endowed with a binary symmetric channel. So in the beginning we initialize the Q networks using some Gaussian noise terms, and we copy the parameters to the target networks. We reset our episodes, and then we'll enter the first while loop until all episodes are done. We will stay in this loop. So we reset the time, and we'll calculate the epsilon for the epsilon greedy strategy, and then we'll start the Markov game at the second while loop. So we increment the time first, then we make an observation. The guide in particular makes the observation, which includes the position of the scout and the position of the treasure at the current time. Then it will find an action either by exploiting the Q function that it has at hand, mainly by the neural network, or it will just uniformly sample over its action space in order to exploit the environment. The scout will then observe this message after it was transmitted over the binary symmetric channel, and will again also choose an action either by exploiting its Q function or by exploring the environment. And then the 2 agents will receive their rewards, and the experiences will be stored in the replay buffer. This will cycle again and again until either the treasure is found or the maximum number of steps is done. After each game, we will sample batches of the stored experiences and use those to compute the DQN network loss and update the parameters by gradient descent. This is the algorithm for the case where the agents can communicate over the binary symmetric channel. And now we will come to the case where the 2 agents communicate over the additive white Gaussian noise channel or the burst noise channel. We can still use the same solution as for the binary symmetric channel, but the difference will be that the observation set of the scout changes from only binary to real numbers. That is because if I put Gaussian noise terms onto my binary symbols, onto 0 and 1, they will become real numbers. However, the more interesting case is when we also have a transmitter alphabet that consists of the real numbers, because then the transmitter has a greater degree of freedom, and this will or can lead to significant performance improvements. So that also means, though, that the guide can now output continuous actions. So we will employ another training method, namely the deterministic policy gradient. And as has been told already in, I think, some other presentations here, the DPG uses a parameterized policy function, mapping the observation to a continuous action. The policy function is approximated by another neural network. On the side of the guide, we now have two networks. One is the mu network for deciding which continuous action to take, which message symbols to send, and then there is the critique, which estimates the value of the action taken. The deep deterministic policy gradient loss is twofold. We have one loss for the critique and one for the policy. As we also have two networks for each of those, we also have two losses, and both of them will again be used to update the parameters via gradient descent. In this case now, we don't use the epsilon greedy strategy, but some noise is added to the messages chosen by the guide in order to promote exploration. And also, before sending the messages, each message is normalized to a power constraint, because the transmitter doesn't have an infinity amount of power in reality. Okay, now we're already at the second algorithm, which is the solution for the guided robot problem for the additive white Gaussian noise channel, which I've talked in before, and it employs the deep deterministic policy gradient. So in the beginning, again, we will initialize our networks. Now we have 3 instead of 2 because we have the policy network as well. And all those parameters will also be copied to the target networks. Then we start our training procedure. So it starts off setting the time to 1 and calculating the epsilon for the epsilon greedy strategy. Then again, we will enter the game loop until either the treasure is found or the maximum number of steps has been taken. So in the beginning, the guide again observes the position of the scout and the goal position of the location of the treasure, and it will decide for a message to send to the scout according to the policy network mu. Some noise term will be added to the message and the message will be normalized. The scout, on the other hand, will observe the message through the additive white Gaussian noise channel or the burst noise channel, and will have a slightly distorted version of the message sent at the guide. And then, according to the epsilon greedy strategy, it will either exploit its learn Q function or exploit the environment by just taking a random action. Both agents will collect the reward, and both experiences will be stored in the replay buffer. After each game loop, we will sample a batch of experiences for agent 1 and agent 2, and we will use that to compute the average scout loss and update the scout network via gradient descent again, and we will use batch number 1 on the guide side to compute the average DDPG critic loss and also compute the average DDPG policy loss, and use those losses to update the policy network as well as the target networks. before going into results of the experiment, I want to take a quick look into the deep neural network architectures and hyperparameters. So the deep Q network and the policy network consists of 3 linear, fully connected layers with 64 weights each, and as activation function in between each layer there's a rectified linear unit, and the number of output neurons depends on the algorithm. For example, for the deep Q network, we have the number of actions as output, whereas for the deep deterministic policy gradient, we only have 1 output neuron, which critiques the action taken. On the policy network, as output layer, we have the dimensionality of the actions, so that reflects the number of symbols that are sent over by a message. On the right side, you can also see the other hyperparameters used for training, and additionally we have the following information. So we train the model for 500,000 episodes with a learning rate of 0.001, and the experience buffer will store 100,000 experiences. Batch size of 128 samples will be used for training after each episode. As a benchmark to test if the network is solving the problem well, we will look at the average number of steps that is needed to solve the problem. And we will compare the network that jointly learns and communicates with an approach that separates the learning and communication, and it will also be compared to the optimal action that is only communicated over noisy channels. So that's kind of the lowest bound on performance that we can expect, because we have the noisy channel on our joint learning platform as well, but we don't know the optimal action, so that is how well we can get. In this case, we are looking at the agents who are communicating over the binary symmetric channel. They're allowed to use the channel 7 times for each transmission. That means they have 2 to the 7 different possibilities of different messages, while only having 16 possible actions. So there's 3 bits of message overhead, which means they have some error finding and correction capability. On the horizontal axis, we can see the crossover probability for the BSC, and on the vertical axis, we can see the number of steps that the agent needs to complete the problem on average. And we can see that the joint learning platform outperforms the separation-based approach by a little bit, although it's not so much in this case. On this slide, we see the results for the additive white Gaussian noise channel and the burst noise channel. Again, we compare the joint learning communication platform with the separation-based approach, and again with the optimal policy sent over by an already known coding scheme named the Hamming code. On the horizontal axis, we have the signal-to-noise ratio, so the higher that is, the more signal and the less noise is in the signal. And on the vertical axis, again, we have the average number of steps. We can again see that the joint learning and communication approach outperforms the separation-based approach. And what's also really interesting is that if we communicate with real numbers instead of only binary numbers, so if the input constellation allows for real numbers as input, we also are quite a bit better. That's the difference between the blue dotted line and the blue line. Okay, so that's it with the first application of this paper. We will now put the effectiveness problem aside and focus on the technical problem of communications. So there's a lot of current literature about supervised machine learning algorithms to find new coding schemes and modulation schemes. But in this case, we want to use reinforcement learning to find coding schemes even without any knowledge about the channel. Therefore, we will reformulate our framework from before as a one-step Markov decision process. So it starts on the left side, where agent 1 makes an observation, which is just some information stored in B bits. The agent will decide on a message to transmit using its policy function, and then will transmit the action or the message over an arbitrary channel that we have no information about. And on the other side, we will receive a distorted version of the message at agent 2. Agent 2 should use its capabilities of the Q network in order to restore the information that we sent on the left side. So we're trying to send B bits of information over the channel, and on the other side restore the same number of bits, the same information. The reward function in this case will be the negative cross-entropy loss, and maximizing the average reward of this problem is equivalent to designing a channel code with minimum block error rate. So actually this problem describes what we are trying to do when we are trying to find a really effective channel coding. Since we only have a one-step Markov decision process, our replay buffer reduces to purely the observation, the action, and the reward, and there is no next observation in the next step because it's only one step. Then there is 3 algorithms that will be compared to each other. One is again the deterministic policy gradient. Here, because of the more simple replay memory, the loss also simplifies as the following. And then the second algorithm is called the reinforced algorithm, and it's based on gradient ascent on the performance. So it takes the gradient of the log policy of certain action multiplied by the reward, and takes that to optimize the network. And then there's the actor critic, which is the third algorithm that will be compared, and that is just a variation of the reinforced algorithm where we subtract a baseline of the reward. Subtracting this baseline reduces the variance of the performance gradient, and thus it allows us to get better results. So now we're coming to the third and last algorithm I will be presenting, and it is the proposed solution for the joint channel coding and modulation. Again, we will initialize all neural networks with Gaussian noise, and then we will start with this training process. In this case, since each game is only of one step, we only have one big loop. So in the beginning, we will observe some random sequence of bits, and then from there on, we will get a message by using the policy network. This message will be normalized and sent over the additive white Gaussian noise channel or the burst noise channel for the agent 2 to observe it. Agent 2 uses its Q network in order to find the best action to the current state, and then the reward will be collected by calculating the cross-entropy loss, and all the experiences will be stored. After each episode, we will sample batches, and then we will compute the average receiver loss first in order to update the receiver network, and then it depends on which algorithm we use on the transmitter side. Either we use the deep deterministic policy gradient approach, or the reinforced approach, or the actor critic approach, all of those which I have mentioned before. Depending on which we use, we will land in that if else clause. We do that again 500,000 times, and then we hope for the transmitter and receiver to be trained correctly on the given model, on the given channel. So these are the results for the joint channel coding and modulation experiment. We can see that the actor-critic approach performs best. So we can see that because the block error rate is the lowest for that algorithm, and also we can see that the two other reinforcement learning based approaches outperform the Hamming coding, which is traditional coding scheme. Okay, so here are the results of the experiments of the burst noise channel. They are, as expected, quite similar to the ones from the additive white Gaussian noise channel. We can again see the three reinforcement learning algorithms outperforming the traditional Hamming coding scheme. And it is also worth to mention that due to the simplicity of the neural nets that we are using here in this framework, the computational time isn't actually much higher than it is used to be with traditional coding schemes. So it's actually quite realistic to use those. Okay, now we are coming to the conclusion. So the group of authors proposed a framework that considers learning and communication problems jointly. So agents in that setting are able to learn solving problems while also cooperating and coordinating each other. This means that agents really learn how to communicate effectively. But the framework is not only able to solve that problem jointly, but also if you put it into a special setting, then it is a generalization of most communication problems studied in literature. So that's usually corresponding to the technical problem. So by the possibility of employing numerical multi-agent reinforcement learning techniques, this framework is able to design novel channel modulation and coding schemes even for unknown channels. Okay, that is it. Thank you very much for your attention, and if there's any questions, feel free to ask them.